So in this video, we're going to be talking about applications of exponential and log functions because these logarithmic and exponential equations can actually be used to model examples that happen in real life. So let's take a look at a couple of examples. In the first example, we have that the mass of a bacteria sample is 2 times 1.2 to the t power grams after t hours. So we know that this function right here, this 2, is telling us how big the sample is going to grow after t hours, where t is your variable. So it's asking us, in part A, it's saying, what is the mass of the bacteria sample after 4 hours? So if we want to know the mass in 4 hours, we can just take the 4 hours and plug that into time, because we know that that is how long it's going to take. So we can take it and plug in 2 times 1.02 to the 4th power, because we have 4 hours. And if you plug this thing to your calculator, you can get your answer. So we can input 2 times 1.02 to the 4th power, and that is approximately 2.16 if we're rounding to the hundredths. Whenever we're talking about examples, we always want to take into consideration the unit. So it's always important to remember the unit that we're talking about. So in this case, since we're talking about grams because it's mass, this is 2.16 grams. Okay, so now let's talk about when will a mass reach 10 grams. So since it's asking about when it will happen, that means that we're looking for time. So we're actually looking for t now. So this means that we have to plug in our 10. So we know that it has 10 grams. And that's equal to 2 times 1.02 to the t power. Because since this part tells us how many grams it is, and we know that it is 10 grams in the moment, we want to try to solve for t. And so remember that in the last video, I told you guys that if you guys have a variable in the exponent, you can apply either logarithms or the natural log, ln. And in this case, but since we have 2 being multiplied to it, we first want to get rid of that. That way we get the part that has the variable as the exponent by itself. So first we're going to want to divide by 2 to both sides, and we're going to be left with 5 is equal to 1.02 to the t power. Personally, I like to use ln better when solving for equations like this, but I'll show you both in this case. And so I'm going to do the ln case and solving it with ln first. So if we use ln, we're going to want to take the ln of both sides. So we're going to take the ln of 5 and also the ln of 1.02 to the t power. And remember the applications, the properties of log and ln, that whenever you have a power, that you can bring to the front. So you're going to have the t ln of 1.02, and that's going to be equal to ln of 5. From here, all you have to do is just solve for t. So we can just divide both sides by ln of 1.02, and then plug this into your calculator. So if we plug this into our calculator, we have the ln of 5 divided by the ln of 1.02, and that is approximately, so t is approximately 81 hours, because we know that it is talking about hours for the unit. If we wanted to use log to solve this equation, we can do the whole change from exponential form to logarithmic form. And that means that we're going to have to change this into log. So we're going to take our base and we're going to write that as log base 1.02 of 5, and that is going to be equal to t. And so again, we're just going to plug this into our calculator. So in our calculators, we're just going to type in log of base 1.2. But to get to that function, we're going to have to click on math and scroll all the way down to where you see log base. You're going to hit enter, and then there you can plug in 1.02 and of 5. Hit enter, and we get the same thing. We get that t is approximately 81 hours or 81.3 hours, depending on if they tell you to round to the nearest hundredths, whole, tenths, whatever the case may be. It'll usually specify. So these are two different ways of solving exponential equations with using ln and log. But exponential equations can also model population growth and population decay. This doesn't necessarily have to be about people. It can also model items like computers, electronics, or even populations like ants and other creatures and animals. So let's take a look at a few examples. The only difference between growth and decay is the sign in between. So the equation for growth is A equals P times 1 plus R to the T power, whereas decay has a minus sign in between. And A usually stands for the future value, P stands for the principal value, meaning whatever the initial amount or the beginning or start amount was. R stands for the rate, but usually it'll be given to you as a decimal. Once it's given to you as a percent. And when it's given to you as a percent, you're going to want to switch it over to a decimal. And T is just how long it's been, the time. So the example says that the number of PCs that are sold in the US in the year 2011 is approximately 350 million, with a growth rate of 3.6% per year. Assuming the rate stays constant over the next years, how many PCs will be sold in the year 2015? So because the question states how many PCs will be sold, that's actually talking about the future value. So A is the future value, and that is what we are trying to solve for. But our principal, our starting rate, our starting initial value is 350. So we can write that down. So our 350, our rate is 3.6%. But if we want to turn this into a decimal, remember that we want to take our decimal and move that 2 spaces to the left. So that's just going to be 0.036 as a decimal. And our time, well, how many years is it from the year 2011 to 2015? That's just 4 years. So that's 4 years. If we plug this into the equation, into the formula that we have for growth, because since this says that it's growing, we know that we are talking about population growth. So we're just going to plug that into the equation. So we're going to have A is equal to 350 times 1 plus our rate. Our rate is 0.036 to the 4th power. And now we're just going to plug this into our calculator and see what it gives us. So our future value A is approximately 403 million PCs. Okay, so in the next one, we have that the size of an ant colony is decreasing at a rate of 0.1 per month. How long will it take until the colony has reached 80% of its original size? So here, since the question is asking how long will it take, how long means that we are looking for time. Even though we're not given the original size of the population, we can assume that the population size is going to be P. So we'll call that P. And if we're looking for it to reach 80% of its original size, that means that the future value is going to be 80% of P. And that basically means that we're going to have to multiply 0.80, and that's because since it's 80%, remember to turn that into a decimal, we're going to have to move that 2 spaces. So that's going to be 0.80 times P, because that is how you can represent 80% of a population. And then our rate we said was 1%. So since this is 1%, again, we have our percent. So to turn that into a decimal, we just have to move that over 2 spaces to the left. So our rate in this case is 0.01. And now that we have all our information, we know that our function is decreasing. So since it's decreasing, we're just going to have to use the decay formula. So we have that 0.80 is 0.80p is equal to p times 1 minus 0.01 to the t power. So we can go ahead and solve for this. Since we have a p in front, we want to try to get rid of the p before we start solving for t. So we can go ahead and divide p to both sides to try to get this term by itself. Now, if we divide by p, we actually notice that the p's cancel out. So we're left with 0.80 equals 1 minus 0.01 to the t power. So if we apply the ln or log, whichever you decide to use, you will get 80 is equal to, I'm just going to bring the t up front since we know it has to come up, 1 minus 0.01. And since we're solving for t, we're going to want to divide by ln of 1 minus 0.01 just to get t by itself. So dividing by 1 minus 0.01. So now we're left with t is equal to 0.80 over ln of 1 minus 0.01. 1 minus 0.01 is just 0.99, so I'm just going to write that. 0.99, and we can plug that into the calculator. So it's approximately 22.2. And we're talking about months, so that's months, 22.2 months for it to grow 80% of its original size. So let's look at the next one. It says that the population size of a country is increasing at a rate of 4% per year. How long does it take until the country has doubled its population? So again, if it's asking you how long, then we are looking for our time. And if it's saying how long will it take to double the population size, then we want to double. We don't know what the population is, so that's p. And our future value, we know that we want it to double, so that's twice as p. And our rate, we said, is 4%. So since it's 4%, we know we want to move that 2 decimal places over to the left, so that's 0.4 as our rate. So now we're just going to plug everything into our formula. So we have 2p is equal to our p times 1 plus 0.04 raised to the t power. And again, we want to solve for t, so we want to get rid of anything else that's being multiplied. So we want to divide by p. So we're left with 2 is equal to 1 plus 0.04 to the t power. So again, you can use log or ln to solve for this, but since I used ln in the other one, I'll use log for this one, just so you guys see another example with this. So this would be log base 1 plus 0.4, well that's just 1.04 of 2, and that is equal to t. That's just changing it again from exponential form to logarithmic form. And just plug this into your calculator and see what we get. So the time is going to be 17.7 years. Okay, so let's do the last one. It says that the number of flu cases is decreasing at a rate of 5% per week. And it says, after how much time will the number of new flu cases reach a quarter of the current level? So we're being asked how much time. So we're looking for time. And our principal, we don't know how much it started off with. Our percent, since it's 5%, we're going to say that this is 0.05. And our new, it's going to reach a quarter of the current level. A quarter, you can represent that by 1/4 of the current level, that's p. Okay, so now let's do the same as before. We're just going to plug it into our formula. Since it's decreasing, we know that it's the one with the minus sign. So we're just going to do 1/4. So 1/4 of p is equal to p times 1 minus the rate, which is 0.05, to the t power. Okay, solving for this, divide by p to both sides because we want to leave the term with the t by itself. So we're left with 1/4 is equal to 1 minus 0.05 to the t power. Now again, just plug it all in. Solve for it. So you have the ln of 1/4. Again, you can use either log or ln. And you have t ln of 1 minus 0.05, that's just 0.95. So we can do that and then divide both sides by ln of 0.95, divide both sides by ln of 0.95. So we're left with t is equal to ln of 1/4 over the ln of 0.95. So again, plug this into your calculator. So since 1/4 is the same thing as 0.25, you can also use that to plug it in. So our t is approximately equal to 27 weeks. So that's how long it will take.